Welcome to our last chapter. Yay! It's open channel flows. So what is an open channel flow? Well, it's any flow that has an air interface. So it's going to be a liquid, and the top of that liquid is just going to be exposed to the air. So that's what have a free surface in contact with the air means. And typically these are driven by gravity. So let's write typically after here. So some examples are rivers, canals, just rainwater runoff, flooding, tsunamis. Just some examples. If we look at this picture of a dam, up above the dam, that's open channel flow. Down below the dam, down here, this is open channel flow with a big, what's called a hydraulic jump. And in between though, where it goes through the pipes and through the turbines, that's all internal flow. So the difference is in pipes, there's no air interface, and so that would be internal flow. So some applications for open channel flow include, again, rainwater drainage. And these applications a lot of times apply more to civil engineers, but they can also apply to mechanical engineers directly. So rainwater drainage, sewer systems, boating, canals, rivers, water species, pollution, spillways, dams, surfing, really anything that would have a open free surface on the top. And you notice I said civil engineers before, but environmental engineers are also very worried about open channel flow. But not only could you as a mechanical engineer be involved in any of these things, there's also some aspects of this that are a lot like aerospace field, shock waves, rockets. So when we talk about waves in the water are a lot like shock waves that you're going to see. If you want more information about the shock waves and rockets and that would be chapter 9. We're not going to cover that, but if you're interested, feel free to read it. So the first thing we're going to do is talk about waves and hydraulic jumps. So if you can imagine, water or any liquid is a little bit like Play-Doh. If you take Play-Doh and you try to extrude it out of the little toy here, you see what happens? It goes straight for a little while, but then something is going to happen that's going to cause it to bend. And a liquid like water is going to bend even more than the Play-Doh is going to bend. It's going to start to kind of buckle. And when it buckles, what happens is you get a standing wave. And that's also, what that means is a standing wave is a wave that isn't moving. So here we're going to study standing waves. We're also going to study moving waves because they're essentially the same. It's just what frame of reference are you in. So here is a picture of a standing wave. If we look back here again at that picture of the dam, right there, going up, there's a standing wave. That's a huge standing wave. Okay. And if we come down here, this is kind of like the Play-Doh example. You have a gate, and underneath the gate there's water flowing out, and after a little while though, it can't keep going at that same rate, it's going to like buckle. And when that happens, you get a hydraulic jump. And you see all these little swirlies here, which you could call turbulence. Those are going to cause losses and erosion, which is very important for all engineers. Okay, so this is so that's one kind of standing wave, okay, a hydraulic jump. Another kind of standing wave is, let's say you put an obstacle in the flow. Well, the water or whatever fluid can back up in front of it, and right here you've got your hydraulic jump, right? And notice though that object is actually affecting the flow a little bit upstream. And that's going to happen more if the water is moving slowly. In contrast, a moving wave, it's very similar, but that would come from, say you drop a pebble into a pond. So it's gonna push the water, that pebble is gonna push the water down. But the water that it pushes down has to go somewhere, right? Because it is incompressible. So it doesn't get smaller, so it's got to move. So it's going to move out, and it's going to cause a little wave around that pebble. So now you've got an area in that wave where the water is deeper there. So when you have deeper water, you're going to have higher pressure, right? And anytime you have a change in pressure across a distance, you're going to end up with a force. And if you have a force, well, that's going to cause things to move. All right. And for both these kind of waves, there's a non-dimensional number called the Froude number that is going to characterize these waves. Okay, so the Froude number, you can think about it, it's a lot like a Mach number. So the slower the water is moving towards the obstacle, the further upstream is your hydraulic jump, right? But as you increase the velocity, that jump's going to get closer and closer and closer to the object, because that velocity, that water is just really pushing on that hydraulic jump. And eventually you get to a point where the wave, that hydraulic jump, is actually can't be in front of the object. It's going to just all be downstream, and that's called the critical flow. Okay, subcritical is underneath that, when you still have one in front, and supercritical, when it's all behind, is determined by this Froude number. Again, non-dimensional, kind of like your Reynolds number or your Struhal number. So your Froude number, the equation for your Froude number is velocity over square root of gy. Okay, g is your gravity. Flow velocity is your v. Again, it's an average. Square root of g, and y is the vertical fluid depth. And this square root of gy actually is your infinitely small wave speed. So if you had a wave that was infinitely small, this is how fast it would go, square root of gy. And so we're going to call that v over c naught, where c naught is your infinitely small wave speed. It's kind of a limit. yc then, we're going to call that our critical depth. And that is going to happen when Froude is equal to 1. Okay, so when the velocity is equal to that infinitely small wave speed. So, like I said a little minute ago, the Froude number then is a lot like the Mach number. And if you think about what I was just talking about, how that standing wave in front of the object suddenly it can't be in front of the object anymore as you increase the velocity, it's kind of like, okay, as you increase the velocity of flow, say around the space shuttle, suddenly, or any kind of supersonic airplane, jet, it's gonna, when the speed of sound, when the jet reaches the speed of sound, the sound waves can't go in front anymore, they all go behind, and you end up at Mach number 1 and you get a shock wave behind your object. So your small wave speed is just like your speed of sound. And so what we study in this open channel flow with regards to waves also applies to when we're talking about supersonic flight. And let me just tell you, the speed of sound in a fluid is A. So stop here and do quiz questions 1 and 2.